Welcome to this presentation on management of smart textiles wastes, recycling and challenges. In this presentation, we will explain the cycle of life of an e-textile and its ecological impact. It underlines the importance of management the wastes from the smart textiles production until the moment after their use. We will analyze the types of the produced wastes and presents various methods of recycling them. It states and concentrates in challenges and problems that can be appear during the process to create a sustainable cycle life of a smart textile. Management of smart textiles wastes. Recycling and challenges. The contents of that presentation are: life cycle of a smart textile, environmental impacts, perceived and programmed obsolescence, sustainable management, development and challenges, and the waste types and recycling methods. Life cycle of smart textiles. The life cycle of a smart textile is a combination of its two parts, the fabric and the devices. The production process, as the rest of the textile life cycle, must incorporate environmental criteria for the reduction of the environmental burden. The low-impacted material selection, alternative processes, improved transport and use, and minimization of impacts in the final treatment of the product's life are few of the considerations of an eco-designed textile. The life cycle of a product is starting with the raw material selection, continues with the finished product and the first launch in the market, and is finishing with its final withdrawal. In the smart textiles, the life cycle includes the life cycle of the fabric and the life cycle of the electronic devices, which are two of the most difficult sectors to approach in an eco-friendly way. A detailed analysis of this life cycle combination helps to understand the waste potential, energy usage and environmental effects in each of its stage. The life cycle assessment, LCA, or life cycle analysis, is one of the methodologies used for assessing the environmental impacts of a product from raw material extraction through material processing, manufacturing, distribution, use, repair and maintenance, and disposal or recycling. The phases of LCA make it possible to identify the way that an activity affects the environment and the size of its impact on the different environmental compartments beyond the boundaries of the production plant. A life cycle assessment can be distinguished in conceptual, that is a qualitative study to identify the most significant potential impacts, and in amplified, that takes into consideration only generic data and covers the life cycle in a superficial way. The scope of the LCA can be gate-to-gate, which focuses only in one process of production chain, cradle-to-gateway, which is an assessment of a product life cycle from resource extraction, cradle, to the factory gate, cradle-to-grave, which covers the range from extraction of raw materials from the earth to manufacturing, product use and recycling, disposal at the end, or by cradle-to-cradle, which has the scope closed-the-loop production. The ecological impact, or footprint, of an activity, is an index that aggregates the whole range of environment changes provoked by this activity. This index indicates the quantity of land or sea productive area that is required, in order to produce the resources that are consumed and in order to eliminate the waste produced. In this way, we can understand the units of area that the activity harms in relation to the area of the ecosystem. It is based on the concept of the carrying capacity of the ecosystems, which is the inherent capacity of the systems to provide material as well as remediate environmental harm. Sustainable management, development and challenges. When we talk about sustainability, we contemporarily talk about humans, society, economy and environment. Human sustainability aims to maintain and improve the human capital in society. Investments in the health and education systems, access to services, nutrition, knowledge and skills are all programs under the umbrella of human sustainability. Social sustainability is the high quality of development of the communities provided the supply of housing required to meet the needs of present and future generations and created accessible local services that reflect the community's needs and support its health, social and cultural well-being. A strong, competitive economy is sustainable when ensuring that sufficient land of the right type is available in the right places and at the right time to support growth and innovation. Environmental sustainability contributes to protecting and enhancing our natural and developed environment, while helping to improve biodiversity, use natural resources wisely, minimizing waste and pollution, and adapting to and helping to decrease climate change, including a global shift to low-carbon economy. Applying these four strategic sectors, simultaneously, interacting with one another in a consistent, committed effort, to urbanization, agriculture, infrastructure, energy, water and transportation creates a sustainable development human system. We can talk about a sustainable development that meets the needs of the present, without compromising the ability of future generations to meet their own needs. The challenge of sustainable development is to move forward in such way that every human will be able to enjoy a substantial quality life without being detrimental to natural resources of the planet. The eco-design is defined the design plan, which it contains, the design for sustainable sourcing with the incorporation of recycles and recyclable materials, the use of renewable energies and the choice of local providers, the design for optimized resource use saving energy, water and resources in overall, improving processes and applying cleaner technologies, the design for environmentally sound and safe product use using less polluting raw materials, selecting materials with low environmental impact and free of toxic products, optimizing packaging and minimize the environment impact of transport, the design for prolonged product use thinking cyclically to keep the product in the best possible condition for as long as possible, establishing fair and responsible business practices, introducing conceptual product improvements, notifying the environmental requirements or the correct use and reuse of the product extending their life even more, and, at last, the design for recycling with the purpose the easier separation of the components, the simpler identification of materials, to reduce the waste generated and improve its final management. Waste types and recycling method. The hierarchy of the wastes based on 6 priorities ranked in terms of what is best for the environment and captures the progression of a material or product through successive stages of waste management and represents the latter part of the life cycle for each product. Those 6 priorities are the prevention, the reduce, the reuse, the recycle, the recover and the dispose. Preventing waste generation involves redesigning products and processes. Reducing waste means to reduce the use of raw materials. The preparation for reuse extends the product's life before they become waste. The recycling is the use of waste materials with purpose to turning them into products, materials or substances whether for the original or other. The recovered energy or materials from waste through processes such as incineration, anaerobic digestion, gasification or pyrolysis can be useful to use or fed back into the electricity grid. And, at last, the disposal is the processes to discard of waste trough landfilling, incineration, pyrolysis, gasification and other solutions to dispose textile waste. Textile and fashion waste can be classified into different types based on their source of generation, toxicity, disposal and discarding are categorized by their nature, solid or soft, or the phase of the product lifecycle that they are produced. Pre- and post-consumer wastes are the waste generated at various levels after usage of the finished product by end consumer and could be any clothing or household article, which has been discarded or not in use for any reason like being worn out, damaged or outgrown. Pre-consumer textile waste, according to Council for Textile Recycling, is the waste generated during production by processing fibers, and the production of finished yarns and textiles, technical textiles, nonwoven, garments and footwear, including offcuts, selvages, shearings, rejected materials and or B-grade garments. Another classification of waste in production is soft and hard wastes. Soft waste is the waste in which fibers are relatively open structure and can be reused at an earlier feed stage. It's generated from bloom to the ring frame and is reusable for producing a low quality of yarn. Hard waste is the waste in which fibers are packed in a closed structure and need additional operations before reusing them with soft waste. These wastes are produced in ring frame, winding, weaving preparatory and during weaving operations. The majority of solid waste originates from other sources during operations like transportation, bale openings, servicing process and housekeeping. The toxicity of the textile wastes is, also, a parameter of classification. Colors, metals, phenols, certain surfactants, toxic organic compounds, pesticides, as well as phosphates are some of the hard-to-treat wastes. Hazardous, toxic and dispersible waste with characteristics that demand different pollution prevention and treatment approach. Hard-to-treat wastes are wastes characterized by their persistent, resist treatment, or interfere with the operation of waste treatment facilities. Hazardous wastes, a subgroup of hard-to-treat wastes, are the metal, chlorinated solvents, non-degradable surfactants and other non-biodegradable or volatile organic materials. Dispersible wastes in textile wet processing are the following: print paste, lint, coating operation, solvent, waste stream from continuous dyeing, printing, finishing etc. At the end, high-volume wastes are, also, one of the challenges in waste management of the textiles industry. Textile recycling is the action of reprocessing pre- or post-consumer textile wastes and use it in new textiles or non-textile products. There are two recycling processes, the closed and the open loop. In the first process, the recycled textile material is used in an identical product. In the opposite, in an open-loop recycling process, the textile recycled material is used in a different product. In general, the textiles can be recycled into fibers, into polymers, into monomers or into molecules different from monomers. The nature of the final recycled product requires different treatments, so, a subcategory of a recycling method is the mechanical and/or chemical processes. The wastes that come from pre-consumer deposits, like industries, are production wastes, unfinished or unsold products. In that case, the composition of the textile is homogeneous and known, something that makes easier the recycle. In the other hand, the post-consumer wastes are mixed and heterogeneous, something that makes the recycle process complicated and more difficult. Moreover, the used fibers could be damaged, and so more fragile. However, in both cases, to recover the fibers, is necessary to separate the textiles by color and material and to remove the hard and electronic parts from the rest of the clothes, as in coated or laminated textiles. After that, the textile must be cut into little pieces, which enter in a shredding machine with rotating metal pins drums to open the textile and recover the fibers. The output is a mix of fibers with different lengths, and the shorter ones can be used as flocks in an open-loop application. Although, to create an identical new product from those fibers, so to have a close-loop application, is necessary to mix the, already used, fibers with new ones to ensure the mechanical properties of the yarn. For thermoplastic materials, another way of recycling is to convert the textile into polymers. That conversion requires a mechanical or a chemical process. In the mechanical process, the pieces of textiles are melted and spun directly or recycled into granulates. In that case, the material must be as pure as possible. The output is granulates that can be used in the production as raw materials, in an open or close-loop process. As in fibers collection, the polymer's degradation is inevitably, so, is necessary to add new material for the creation of a yarn with the same mechanical characteristics. In chemical dissolution process, the textile pieces are dissolved in a specific solvent, where the fibers are converted from synthetic polymers to cellulosic fibers. The output is a dissolved polymer, which can be spun using a solvent spinning process to recover a fiber of the same nature as the input one. The advantage of this process is it can handle contamination and fiber blends, as it is possible to dissolve only a part of the blend. It is also a solution to remove coatings, dissolving only the fiber or only the coating. Another recycle way is to convert the synthetic polymers of textile into monomers by a chemical depolymerizing process, where pieces of the textile can be depolymerized in various ways to create output monomers, with the same quality as the virgin ones, that can be used in industry of textiles or plastics in an open or close-loop process. This is an infinite recycling process, because there is not degradation in quality and the impurities can be well removed from the texture from the moment that they cannot be depolymerized. From the other hand, in recycling textile into molecules there are chemical processes as pyrolysis, composting and fermentation. In pyrolysis, the pieces of textiles are heated at a very high temperature to be degraded and converted to gas, oil and carbon. The input is any organic carbon-based material, including biomass, plastic and textiles, and the output are various mixed gases, oils or carbon that can be used as fuel or as feedstock in the production of chemicals. This application can be, only, an open-loop application, has as advantage to recycling fibers or blends, which cannot be recycled otherwise by other used technologies, but is not developed on an industrial scale in the textiles. In the processes of composting and fermentation recycling, microorganisms transform organic material into molecules, thanks to fungi, yeast or bacteria in the presence of oxygen, water and nitrogen. The input could be cellulose-rich feedstock and mixed textile wastes, and the output is a range of fuel molecules, chemicals and non-cellulosic fibers that can be used as fuel or as input in other industries. In conclusion, in the sector of the smart textiles, it is important to understand and approach the textile with its two different natures. In the recycle procedure should be separate the fibers part of the texture from the electronic parts in order to improve the processes that already exist today for the simply textures in one part and the devices in the other. Furthermore, selecting the right recycle process, the output product can become the raw material for the production of other simpler or more complex products.